What's up, everybody? I made a thing today. So we're just gonna take a quick look from top to bottom of it, and then throughout the video I'll go over everything in more detail. Starting at the bottom, we got some feet made out of some flexible material, 3/4 inch hydrocarbon foam. Then we come up to the tripod part of it that holds all the legs. Moving up, 4-foot section of that 3/4 inch. Then we get to the LED driver box, the pivot joint for the diffuser, the heatsink fan, and the LED, and then just a cheap umbrella spray painted white as the diffuser. Alright, so let's get started. For those of you that actually want to make one of these, just check down in the description. I should be selling most of these parts online, 3D printed. Alright, so we're going to start going over the actual modeling I did, and I guess we're going to start from the ground moving up to it. So right here is the model of the feet. It's extremely simple. Just start with a sketch and then revolve it. So bam, revolve it, and there's the foot. And this was printed in TPU, which is a thermoplastic polyurethane. It's a flexible material that can be printed, but it's not like extremely rubbery. It's like a very stiff kind of flex, and it's actually incredibly strong, so I figured it'd be appropriate to do for the feet. Then we'll move up. This is the industrial size butt plug that holds all the legs. Here, we'll walk through the steps. Pretty straightforward. I did intend, this was printed out of PLA, so the only thing, everything was printed in PLA except the feet, which was TPU. I did originally intend to have all 3 legs fold together, but that was taking a lot of time and a lot of design it was taking too much time to try and design, so I just decided to go with the static, holding the 3 legs at like I think a 60-degree angle or something like that. Alright, then moving on up from there, you get to this this little ring right here. That's got the 2 countersunk holes for the screws, the fixed ring. Then you get to this guy that rests on this flat edge right here, rests on top of that ring and pivots, and then this flat edge right here will be attached to the LED driver box. And we'll play that through. The LED driver box. Let's play through this. Most of these models, I didn't actually model them correctly. What you're really supposed to do is, make parameters for yourself right like that, and sketch fixed dimensions, and just basically, you're supposed to model it to where if you want to go back and change something, it's very easy and it doesn't ruin the whole model, or you don't have to remodel a whole part of it or something. For a lot of these, just since they were my own and relatively simple compared to super complex models, I just did it on the first try, just quick and dirty. And I didn't really sketch a lot of dimensions. I was just putting them in one by one. So if I wanted to go back and change something in this, it would be very, very annoying to do because of that. But I was able to get it on the first try, and everything fit properly, so it wasn't a huge deal. Alright, and here's those the little gear pivot point up at the top. This part came out great. And I really wish I could be more specific about the fasteners and nuts and bolts that I used to assemble all this and how I modeled it around. But the fasteners came from that place where all of our hoarder tendencies tend to collect. Alright, and here's the knob that goes to the part I just showed. And here's the smaller knob. Yes, I am an idiot. I modeled this backwards. I could just mirror flip it, but it's not that big of a deal. You want these concave parts to be what you push on when tightening, but obviously that's not the case here because the hex part's on the bottom. And here's the last one for mounting the heatsink that holds the LED on it. You may notice I did a red and a blue color for the PLA parts. The blue was just all the pieces that had to do with the electronics. The red pieces were just all have to do with, just holding everything. Alright, so all the pieces are done and they're ready to be assembled, but I wanted to talk to you all about the designing of them. I'm pretty fucking awful at designing, but I do know a few things about 3D prints and how you want to design them so that they can be the strongest possible, for what it is. It's just plastic. So if you're wondering why the teeth, it has to do with the strength of the layers of a 3D print. So the weakest point of a 3D print is any force going perpendicular between the layer lines. So let's say, these are the layers of your 3D print. Any force, any compression force or tensile force in these directions, perpendicular to the layer lines, is its weakest. It's just going to want to separate those layers. So, and the strongest of 3D print is any force going parallel with the layer lines, because obviously there's going to be way more friction trying to slide those layers apart like this rather than slowly stretching them apart. So what that means is, if you look at these teeth real close, focus, motherfucker. The layer lines run with the teeth. So what that means is, like, let's say if there wasn't any teeth, and we just used the clamping force of this knob right here to squeeze these parts together and hold. Why is that weak? It's gonna wanna, because it's pulling, like we said, it's going to be compressing. Now, compression is better than the tensile, but what happens in the compression of these layers is that they'll wanna buckle and separate like that. And that's, yeah, like I said, that's better than the tensile force pulling it apart, but it's still not the best, because you start just putting, even a nominal amount of force and compression, just tightening them together, it's going to want to separate like that. So with these teeth, rather than putting all the force laterally or perpendicular to the whole setup and having that force be the holding force, we know that it's the strongest radially when it wants to turn, because that's where the layer lines are moving with it. And if you look, so basically, if you're applying, 30 foot-pounds to this, How's the force on this teeth? The force on the teeth is moving parallel to the layer lines. So it's incredibly strong, and we're not relying on any force to hold those teeth together. We can just tighten it. You just finger tighten it. So you don't even that's it. And then trying to spin it, and all that force, all that radial force is just being applied to those teeth, which not only is a large surface area, but it's also in the proper direction for the strength of these layers. I think it came out pretty good, huh? So this is the ring that printed up. Slide it on here. I'm gonna put some screws in it, and then that's gonna be the fixed ring, and then the LED box that we were just looking at slides right over this, has a ring on the back, slides right over this, and it's gonna rest on this ring. But I'm leaving the top assembly that we should have seen already, this guy, loose on the top so that the whole thing can swivel. And rather than just wrapping up the wires around it, the box is going to be able to swivel around with it. It's pretty smart, eh? Smart like a fox, maybe? Could you imagine doing tool reviews or tool teardowns and never touching on the extremely rare, never before seen rare breed of the albino Makita? Imagine. Alright, let's test it out. Yeah. Alright, so we're gonna get into the meat of her, and I'll just explain what's going on overall, and then we'll break it down a little bit more. So for the input, I found this old had an old HP laptop. This is a power supply for it. Its output is 19.5 volts and 4.62 amps, so a maximum of 90 watts basically. And that input voltage falls just within the range of the LED driver I got in here, so that worked out. And then this is the 100 watt LED cob, but I thought I thought that when it said 100 watts that it meant it actually draws 100 watts of power. That's not the case. Apparently these things, what it means is, I guess it's the equivalent of a 100 watt light bulb, I think. I'm not sure. Somebody correct me on that, because when I was running it, when I got it to like max brightness, it was really only drawing about 40 watts of power. Alright, so let's crack open this LED driver. Alright, here we go. So I guess right on the front we have this pot right here and the switch, obviously on-off switch, and this pot is gonna control the output signal to the LED, and I think it's PWM. So yeah, so that's just gonna increase basically the brightness just by increasing that signal strength to the LED. Alright, and the whole point of this LED driver, I mean, it obviously in the name it drives the LED. But the problem, like why you can't just hook up just like the power supply to it with a resistor in series, is because
LEDs, they have a dynamic load, which means like when you first put a load on them, they have, you know, a load, a resistive load basically taking power, but as it heats up, its resistance goes down, which means it starts drawing more current, and then the current will just destroy itself. So you need a driver for them. Basically what this is just a constant current supply. I hope I'm explaining this correctly. So this is just supplying constant current to this guy, making sure that it's getting the correct power, because the voltage on these surprisingly is not that important. You can actually, I was testing it with my power supply over here, you can put a 20 to like 30 volts across this and it's gonna light up and be fine. So the voltage doesn't matter, so that's really helpful in making a constant current application, because you can adjust the voltage within a certain range to get the current needed, and then maintain that current needed to drive the LED. And right here, this is the input from the power supply, and I did some strain relief right here because it's the only solder joint, so I really didn't want anything tugging on those, because if it rips up those contacts, it's fucked. Great board, actually. They had, linked down in the doobly-doo, they had pins for the on-off switch, the potentiometer, a fan, actually, a fan, and then yeah, a nice beefy screw terminal for the LED contacts. Heatsink for that MOSFET? No. Maybe. I'll have to look that up. Alright, let's get it back together and test her out. Alright, set to the lowest brightness for when we turn it on, so there's no inrush of just massive amounts of current. Alright, but that's nothing. Let's crank this up. Wait, shit. Fan's not running. Alright, let's try it now. There we go. Alright. Trying to get some airflow under there. Alright, let's crank this up. Can you see it? Yeah. Let's crank it up. Holy shit. What the fuck? Damn, what does that look like on camera? Whew. Fuck. I'll just see a bunch of squares. So it works. Surprise, surprise. Yeah, it wouldn't look this neat if I didn't think it was gonna work. I did a lot of testing, so. So, I was wondering how much of a heatsink and fan did it actually need. I knew it needed some heat dissipation, for sure, no doubt. But I was wondering if like you could get away with a big heatsink, or maybe a smaller heatsink and a smaller fan. No. With the fan on, the aluminum stays really cool, so I was like, oh, maybe it's overkill. Maybe it doesn't need it that much. It absolutely does, because earlier when I had the same fan problem on one of the contacts got loose, and the fan didn't come on, and I didn't think about it for a minute, and I left the LED on for like 30 seconds. The whole heatsink was burnt. I burned my fingers on it. It was hot. Alright, this is what it looks like before. And let's turn it on. Yeah, that's much better. And ideally you'd have two of them, like 120 degrees apart, and then it would come in from both sides basically and reduce all shadows and make it even brighter, and so you can see everything clearly. Anyway, thanks for watching.